Сейчас пусть так будет, надо решить.
Расширьте.
Решить, значит, решить.
Ну хорошо.
Пусть так. Выключи.
Ну да, мы же с вами. Greeting for everybody. This is the lecture on biophysics. Lecture theme is biophysics analysis and modeling of human tissue electric properties and effects of electromagnetic factors action. Here you can see the list of the goals of lecture and list of the objectives of the lecture. What are the goals? The specification of electromagnetic factors and quantification of their action on matter for analysis and modeling of factors action effect in human tissues. Quantification of human tissues electric properties and processes to develop evidence base for physics diagnosis and treatment methods correct choice. And objectives are electromagnetic parameters and basic laws nomenclature review, electromagnetic factors identification, application of electromagnetic factors in medicine, and physics methods of registration of electric processes in human structures. This is the list of the lecture points. These points are in correspondence to the goals of lecture and its objectives. First of all, let's review of electrodynamics parameters and basic laws nomenclature, and electromagnetic factors matter influence. Under number 2, the second point is about applications of electromagnetic factors in medicine. Human tissues, electric properties and processes analysis and modeling is the third point. And the fourth point is the physics methods of human electric processes registration to diagnose structures' functional state. We make conclusion, the summary of the lecture, and you'll be suggested the list of the scientific literature you can take material to support your learning on this theme as biophysics analysis and modeling of human tissues electric properties and effects of electromagnetic factors action. So we start from the first point. It is the introduction, review of electromagnetics, electrodynamics, parameters and basic laws nomenclature. Excuse me. Electrodynamics generalizes electricity and magnetism. Electricity is the set of physics phenomena associated with the presence and flow of electric charges. Magnetism occurs due to electric currents. Electrodynamics is physics section that deals with rapidly changing electric and magnetic fields. Electric charge is the property of the objects to interact at distance with force far greater than the force of gravity. The atom electron charge is referred as elementary negative electric charge. The atom nucleus proton charge is elementary positive electric charge. The magnitude of these two equals to 1.6 times 10 to the power minus 19 coulomb. The macro unit of charge is the coulomb, equals to the charge of such number of electrons of the protons. 6.2 times 10 to the power 18. This is the charge of one coulomb. Unlike charges attract and like charges repel. Electrostatic force is calculated by Coulomb's law. You can see this formula to calculate the force of the interaction of two charges. It is directly proportional to the product of the magnitudes of the charges and inversely proportional to the distance between charges squared. And this is similar in its configuration, that formula, to the formula for the gravitational force that is developed at the interaction between the, for example, bodies on the surface of the Earth and Earth. Electric charges produce electric field in their vicinity. If another charge, probe charge, Q, is present, it experiences a force. The force on the positive unit charge is referred as electric field strength at the point where this probe charge is placed. And the magnitude of the electric field strength equals to the ratio of the force exerted by electric field and the magnitude of the probe charge. Since the force is a vector, the electric field strength is also a vector. Positive charges experience forces parallel to the field strength vector, and negative charges experience forces opposite to the direction of the electric field strength vector. So here you can see the force and the strength lines of electric field and their relative directions. The potential energy of two charges, Q small and Q capital, these letters denote that two charges, separate by distance r, is of this magnitude. So we can describe this situation when the probe charge is placed into the electric field that is developed by another charge as the interaction between these two charges. And consequently, we can write down this formula for the potential energy of this kind of the interaction. If we divide this potential energy of the interaction between charges over the probe charge magnitude, we obtain electric field energy characteristic. That is electric field potential in point of the unit charge, in point of the unit charge. And potential difference is referred to voltage. As in this particular case, you can see that the electric field is non-uniform. This means that the potentials are different at different points. So potentials difference is termed as voltage, and this may be measured by placing here two electrodes and connecting these two electrodes to the voltmeter, and voltage will be measured and reveals the presence of a non-uniform electric field into the space of investigation. So, and look, we can say that the electric field, it is the kind of the matter. The distinguishing feature of the matter is the energy the matter object carries, possesses, stores. And this is not different when we talk about electric field. We can say about electric field energy that is stored, carried by that kind of the matter as electric field. So, and by this means, the energy may be converted into the kinetic energy of motion of the probe charge into the electric field. And the magnitude of the work that electric field can do moving the probe charge may be calculated by this formula. So you can see this equation showing by how one kind of energy, electric field energy, is transformed into another kind of energy. It is the kinetic energy of motion of the probe electric charge into the electric field. And this process is termed as the work done. But actually, it is the process of energy transformation from one form, from electric form, into mechanical one. You can see here the configuration of two flat plates that are parallel to one another and that are separated by the space of this distance. And you can see that these two flat plates are connected to the direct current supply, to the battery. And by that means, these two plates are charged. From the battery, the positive charge goes and stored at one plate, and negative goes and stored at the second plate. And these two collections of charges on the plates develop into the space between the plates their electric fields. These fields interfere and becomes to be a resultant electric field. And you can see that these resultant electric field strength vectors are parallel to one another and are of the same density within the space between the plates. Such kind of electric field is identified as the uniform electric field. And you can see the strength of the uniform electric field equals to the ratio of the potentials difference at the plates over and the distance between the plates. And this configuration of the parallel flat plates is named as the flat plates capacitor. And the property of the capacitor to store electric charges on the surfaces of the plates is termed as the capacitance. Actually, the definition of the capacitance is this as the ratio of how much charge is stored to the potentials difference developed potentials difference between the plates. And as any electric field, this field stores energy of this amount. This formula gives the opportunity to calculate how much energy is stored at the electric field developed by this kind of the capacitor. A material with internal free charges is defined as electrical conductor. The first type of conductors are metals with electrons as free charges. The second conductors type are electrolytes with ions as free charges. An electrical insulator is a material whose internal electric charges don't flow freely. You can see that now we can look inside the substances, inside the material objects made from, and classify. The criteria to classify the materials, the substances, is the kind of the free charge that presents at that material. And these are two insulators and conductors. Electrolytic conductors are of the most our interest. Why it is so? Because actually all biological liquids are electrolytes, are solutions, and you can see. And what is the solvent of that solutions? The only one. It is the only water playing the role of solvent for the biological liquids, in particular in human body. And you can see that water, in some cases, to be consisting of polar molecules. You can see that within the molecule, the electric charges are separated at opposite ends of the molecule. And this is the kind of electric dipole. A little bit later, we will talk about electric dipole more detailed. But now, let's recognize this process as dissociation of some molecules into the water solution. In particular, this table salt molecule. It is polar as well, and the positively charged ion of sodium is attracted by negative charge of the water molecules, and chlorine, to be negatively charged, is attracted by positive poles of water molecules, and by that means to be attracted in opposite directions, the water breaks down, dissociates this molecule, and what are developed, the sodium positive ion and chlorine negative ions into that sodium chloride solution. And this becomes to be free, so consequently they can carry electric current as electrons into the metal, but these are different from the electrons. And this difference is revealed by this term as electrolytes or conductor of the second type. And this is the example by how biological liquids, the liquids into the structures, interstitial liquid in particular, cytoplasm, exoplasm, are electrolytes, are conductors. And some words about electric current into the conductor. Independently, would it be the first type conductor, or would it be the second electrolyte conductor? Doesn't matter. The regularities of electric current through the conductor are same. In particular, first of all, what is the electric current? Electric current, it is the flow of free charges into a conductor. It is the motion of electric free charges into the conductor in one preferential direction. These charges carries electric charge, resultant electric charge, through the cross-section of the conductor within time of the observation of the electric current. And how much charge crosses the cross-section of the conductor per unit time, it is just the quantity electric current, it is measure for the electric current. And the conductor influences the electric current. It is understandable by how the charges meet at their pathway other present particles and collide with them. And this looks like resistance to the flow of electric charges. So the electrical resistance is the measure of the ability of the material of the conductor to prevent electric current, to resist the electric current. And the formula, for example, in case when the cross-section of the conductor is of the same area along its length, this formula gives the opportunity to calculate the resistance of the conductor. And what should be mentioned else? For the current to exist, the potentials difference should be developed at the opposite ends of the resistor of the conductor. In particular, resistor should be connected to the battery, and electric current will go through resistor. And it is experimental data obtained by Ohm that electric current is directly proportional to the voltage applied to the resistor and inversely proportional to the conductor resistance. So one more basic, and look here. This is the illustration by how ions go through the electrolyte, by how that kind of the free charges develop electric current into the electrolytes. Electric charge experiences drag force passing through electrolyte viscous medium in accordance with the Stokes law. And this plays the role of the resistance of that kind of the conductor. And this is the force that is exerted by electric field developed into space between these two electrodes where electrolyte is placed to absorb electric current into it. And the force on the ions into electric field is expressed as the product of the charge carried by the ion and the strength of electric field developed between the electrodes. By how? By connecting to the battery. By application of this voltage and the strength of electric field and voltage applied, these are related with one another, and equation under number 1 shows that relation. At particular strength of electric field, the electric field force becomes to be equal to the Stokes force, and the velocity of the motion of the ion becomes constant and of this magnitude shown by the equation 3. This is the first description by how ions go through the electrolyte. At this strength of electric field, they can go with this constant velocity. And look, what are the characteristics that are involved? It is the radius of the ion, the eta, Greek letter eta, it is the parameter termed as viscosity of the electrolyte, and this is the charge carried by electron, and this is the strength of the electric field. And let's look from electric current point of view at this motion of the ions. We can say that this motion of the ions can be considered, and it is, as electric current when the voltage is applied and the conductor is of this resistance. Resistance equals independently on its type of the conductor equals may be calculated by this equation after we substitute this at the equation of the electric current. We obtain this, and when we take in account that the 1 divided by the resistivity is the conductivity of the conductor, and this relation between the voltage and the strength of electric field. And let's take this one more measure of electric current. It is the electric current magnitude divided over cross-section area of the conductor. In our case, this cross-section area of the conductor, it is the area of the electrodes. The area of the surface of the electrode. And after that, we can write down that Ohm's law just for electrolytes, that the current density is directly proportional to the electric field the electrolyte is placed into. Current into the electrolyte is developed by two kinds of the ions, positive and negative, so consequently we should add to the Ohm's law the density of the current developed by the negative ions. And finally, we obtain this formula, Ohm's law for electrolytes. And let me pay your attention that electrical resistance of electrolyte depends on the volume of the electrolyte. The greater volume, the less resistance, the better conductor is that electrolyte. When we talk about the tissues kinds, we can find water and solutions rich tissues. In particular, it is connective tissue, blood. of the half of its volume is represented by the liquid part. It is the plasma. So the blood is the best conductor into the human organism. As well as skeletal muscles are of big enough amount of solutions. So skeletal muscles are good conductors as well. So, and this is proved, it is evidenced by this formula. The greater volume of the electrolytes, the better is that electrolyte conductance. So, and one more from the basics of electrodynamics, it is this configuration of two electric charges that are of the same magnitudes but separated by the space of distance d. This is termed as the electric dipole. And the characteristic of this electric dipole, quantifying its property, is the electric dipole moment. It is the product of the electric current and the distance between electric currents. So, and the electric dipole develops into the surrounding electric field of this strength, so, and look, when electric dipole is placed into the external electric field, the pair of forces are exerted by electric field, and these forces are of different points of their application. So they develop the torque, and this torque is the measure of the ability of this pair of the forces to rotate, to change the position, to orientate the dipole into the space of the electric field. And the magnitude of the torque depends on the electric field strength, depends on the electric dipole moment, and depends on the initial position of the electric dipole. And when this orientation of electric dipole into the space of electric field may be considered as one more kind of the transformation of energy from electric form, from electric field energy into the potential energy of the dipole when it will be aligned into electric field. This becomes different electric dipole. Why? Because it possesses extra energy, potential energy of its position, new position, into electric field. And how much work is done, should be done to orientate, to align the dipole into electric field, this may be calculated, and you can see this depends on initial position of the dipole. And look here, where we can, why do we talk about the dipole? Because some tissues into the human body, their molecules, it will be better to say, the tissue consists of, are represented, maybe modeled, by this configuration as electric dipole. Look at some organic molecules, in particular the electric charges are placed, are positioned within the molecule at its opposite ends. And by that means they are separated by particular distance, but they continue to be at a molecule of the tissue. And this kind of the molecules is termed as the polar molecules. So, and when such kind of the dielectric is placed into the external electric field, this electric field does work under the molecules and orientate molecules along the vector of the strength of electric field. So, the polar molecules are aligned in an electric field with the positive end to the of the molecule preferentially pointing toward the negative plate, it is understandable, and the negative end of the molecule directed toward the positive plate. Molecules with minor symmetry, like oxygen, carbon dioxide in particular, have no permanent dipole moments. Even if there is no permanent dipole moment, it is possible to induce a dipole moment by the application of an external electric field. This is called polarization. And the magnitude of the dipole moment induced is a measure of the polarizability of the molecular species. Non-polar molecules are polarized by external electric field. Then electric field orientates dipoles developed. So same behavior, but the only one step that is required to make a non-polar molecule polar molecule. This is the polarization of non-polar molecule. And look by how both kinds of molecules will behave themselves into the alternating electric field, the field of the periodic change of the orientation of the vector of the strength of electric field from one to opposite. In particular, two electrodes that are connected to the battery with the change of the voltage with this in particular frequency, and this is the change of the direction of electric field orientation with time. And look, periodically the torque developed, exerted by electric field changes its direction, and consequently the molecules are set into such kind of rotation, periodic rotation, clockwise and anti-clockwise direction of rotation. One more time, this is the process of the energy transformation from electric form of this electric field independently, that it is alternating electric field in this particular case, into mechanical form of the motion, extra motion of the molecules. And this reveals by the heating, by the rise of temperature of the dielectric. So you can see that to be placed into alternating electric field structures developed by as dielectrics, developed by consisting of such kinds of molecules not to be conductors, may be heated as well as the electric current hits the conductor going through it. So, and this is just the physics that at the core of the treatment by the structure of the structures of the human body by heating. Thermal therapy. This is the you should recognize what happens actually when you implement that or another physics method to treat the patients. You can see that physics explains you by how the factor influences the structures molecules. And now look here, magnetic fields are produced by electric currents. Let's consider this one more physics factor, a magnetic field. Macroscopic currents in wires or microscopic currents associated with the electrons in atomic orbits. The magnetic field is defined in terms of force on moving charge in the Lorentz force law. Magnetic field characteristic quantity, and this force on the moving charge, probe charge with that velocity, this force is determined, and then the strength or induction of the magnetic field may be calculated as well. One more physics factor, and this is one more kind of the matter. So electric field carries energy, and this is the distinguishing feature of the matter, as well as magnetic field to be the form of the matter existence carries energy as well. And energy stored by the magnetic field is of this magnitude if the magnetic field is developed by the current going through the coiled wire. This is the coil of inductance. The coil of inductance, and the energy that is stored into the inside this coiled wire space is of that magnitude. So one more kind of the physics factor, and electromagnetic waves. If the motion of the charge, this charge Q, is of oscillatory nature, so the charge oscillates up and down. For example, the variation of electric field strength and magnetic field induction will also be sinusoidal. The oscillating motion, you might remember, may be described by this equation of motion. And as the electric field vector and magnetic field vector follow that oscillations as well, with the same circular frequency. Electric and magnetic fields are linked in a continuous mutual transformation and represent electromagnetic field phenomenon. Changing electric field produces changing magnetic field, and changing magnetic field in turn produces the changing electric field. And these two fields are not located nearby the oscillating electric charge. This combination propagates into the space with this velocity denoted by c and equals into the vacuum 3 times 10 to the power 8 meter per second. And this combination propagating into the space in all directions is termed as electromagnetic wave. One more time, you can see this combination carries energy, electromagnetic wave energy that is carried by electric and magnetic fields. And electromagnetic field propagates in matter with the ultimate speed. This depends on the matter, this dielectric constant, and these are the matter magnetic permeability, and these with the zero index are electric and magnetic constant that are known. And electromagnetic energy is carried by electric and magnetic fields propagating through the space, as it was said already. And in accordance with the Max Planck theory, electromagnetic waves can be considered, it will be better to say, can be modeled as a flow massless photons carrying elementary energy directly correlated with the frequency of electric and magnetic fields vectors oscillation. And this elementary energy, elementary portion of energy is termed as the photon. Massless photon imagined as the particle without mass but carrying that amount of energy. So, two models of models for the describing the propagation of electromagnetic energy. Electromagnetic wave is one model, and photons flow is one more model. And look, the transmitted energy is dissipated due to any losses within the medium. The power dissipated per unit volume in non-magnetic uniform materials exposed to electromagnetic fields can be expressed by this equation under number 1. F is the frequency dielectric loss factor of the heated material. Look, you can see that the energy can be transformed when electromagnetic wave goes through the matter. And one more time, this is from electromagnetic wave energy. This goes to the thermal energy that is stored at the material. More power is dissipated in the material at higher frequencies. The penetration depth of an electromagnetic wave is inversely proportional to the wave frequency and the attenuation factor of the material. Wave penetration into any material can be defined by the penetration depth, when the ratio of the wave amplitude to initial amplitude is 1 over the charge of the electron. Penetration depth is you can see, depends on the frequency inversely proportionally. Electromagnetic factors matter influence is listed here. Look, electric field stores energy, and this energy is converted into the heat of the materials that is placed into electric field, and the amount of energy depends on frequency of change of electric field, strength, vector, direction, and depends on the value, magnitude of the electric field strength. Magnetic field, one more time, stores the energy and can produce heat into the materials. Electric current hits the conductors, it crosses, it goes through, and electromagnetic waves, short waves, microwaves, transfer energy, and this energy, one more time, is converted, can be converted into the heat of the substances as well that electromagnetic waves go through. Electric properties of human tissue are listed here. You can see the muscle, bone, skin, blood, and other conductivities, and you can see the blood is the best conductor because of the highest, of the greatest conductivity. So you can see that these two electric properties and electromagnetic factors provide the possibility, the opportunity to influence the functional state of the structures of the human body. Electric properties of human tissue at different frequencies, are shown here. Frequencies. You can see at this frequency, penetration depth for the electromagnetic waves, conductivity of different kinds of the tissues are different, and this difference depends on the frequency of electromagnetic field of electromagnetic waves. And now we are ready we are prepared, it will be better to say, after that short brief review, to describe, to recognize by how electromagnetic factors are applied, implemented in medicine. Electric power can be transformed into heat as required into the body tissues if the frequency of the current is high enough for its passage not to be accompanied by an excitation effect. This condition is found to be satisfied if the current with a frequency higher than 10 to the power 5 Hertz are applied. Not less frequency can be used. The energy produced in the oscillator of high-frequency medical heat-producing devices is transferred to the site of the treatment by the patient socket. The oscillator receives its power from a direct voltage supply. or mains transformer. To avoid electric shocks, the oscillator supply voltage must not pass into the patient circuit. Diathermy is the one from several thermal therapy methods. Deep heat is produced when electromagnetic energy is converted into heat as it passes through body tissues. Energy sources include high-frequency currents, electromagnetic radiation. The temperature rise depends on the properties of the tissue, the specific heat, thermal conductivity, and the length of time that the heating modality is applied. And this is illustrated by this diagram. You can see that inductive coil producing magnetic field is the most effective to treat by heating the good conducting materials or substances, tissues, it will be better to say, as muscles in particular. The capacitive plates is preferential to be implemented to heat the fat-rich tissues. And this is effective to treat by heating muscles and bones as well. And microwave modality is preferential for the fat-rich tissues as well as for the muscles. Now, look here. The application of microwave radiation or of short-wave diathermy with capacitor plates at a frequency of 24 MHz can provide selective heat to deep tissue and superficial muscle. Heat is produced by the dipole effect, this dipole effect of the periodic orientation in opposite direction of the polar or non-polar molecules. Charged particles within the membrane align with the field. The movement produces heat. But as for the solution rich as muscles, tissues, we can say that with this frequency, the charges start to oscillate, and this leads to the rise of temperature as well because of the collisions between the particles into the solution. So consequently, would it be the dielectric kind of the tissue, or would it be a good conductive tissue? In both cases, this shortwave diathermy with capacitor plates will lead to the temperature rise, will lead to the heating of the object, of the structure of the human body. And you can see by how this is realized in medical practice. Two electrodes and the electric field, and this amount of heat is released into that or another kind of tissue. And you might remember the table showing that characteristic of electrical properties of different tissues. Look here, short-wave diathermy with an induction coil applicator. It administered at 27 MHz can hit superficial muscle. A coil is housed with a drum. Current flowing within the coil produces a rotating magnetic field. Magnetic field produces eddy currents in the tissues. Eddy currents cause friction that produce heat. Although rare, cables are sometimes used in place of drums. Drum applicator, and how much heat is produced you can see expressed by this formula. So different tissues require different magnetic field strength or inductance, yeah. So, and different time of the procedure. So you can see that the physics gives you the evidenced base to make absolutely correct choice to treat the different parts, different kinds of tissues of human body structures to avoid harmful or it might be dangerous effect on the human body structures to destroy the functions of the structures. And look here, microwave overheats tissues by means of microwave frequency electromagnetic field. Microwaves are electromagnetic waves of a wavelength from 0.1 to 100 centimeters. They can be generated by a special generated lamp called a magnetron. Microwaves undergo reflection, dispersion, refraction, and diffraction on various complicated tissue structures. About 50% of the microwave beam applied to the skin is reflected. The rest is absorbed by tissue at depth of only 6-8 centimeters. Microwaves cause an oscillation of ions in electrolytes and molecules in polarized dielectrics and in this way create heat. The most overheated are tissues containing a lot of water, such as blood and muscles. Fat tissue containing little water is only slightly affected. Diathermy can't be can't be implemented in these cases. When there is cardiac pacemakers, artificial cardiac pacemakers, metal implants or metal jewelry, be aware of body as this you can see, and these you should take in account to make your choice as the doctor to implement that heating therapy, thermal therapy methods. This can be implemented at these cases, in these cases, at these conditions. And now look here, you can see the illustration by how the physics method may be implemented, may be applied for non-invasive caring medicals into the human body, inside the human body, through the skin, not as injection, but look and recognize that ionophoresis as a non-invasive method of propelling high concentrations of a charged substance, normally medication or bioactive agents. Two electrodes are placed on the surface of the skin, and one electrode is considered as the active, and under this electrode the medication is placed in form of the solution carried by the molecule, carried by the ions, carrying that ions carry the drug that is goes into this inside the human body, and because of the presence of one more oppositively charged electrode, and these ions develop electric current between the electrodes, and by that means they go inside and carry that treating substance. You can see that one more illustration, and it is understandable that you should take in account what is the ion charge sign. So if it is the positive, that kind of the drug should be placed under the positively charged electrode, and it will go toward the negatively charged electrode. So it is ionophoresis, non-invasive method of propelling high concentration of a charged substance. And you can see ionophoresis is a method of delivering a topical anesthetic with mild electric current. And you can see configurations of non-clinics realization of ionophoresis. Ionophoresis is best suited for injured areas which are very near to the skin. Tissue deep inside the body is too far for the effectively transported chemicals to effectively penetrate. So, and you can see that examples where this ionophoresis is the most effective treatment for running injuries, in particular. And you can see the drugs, ions list, and what are the sign of that ions. And consequently, this determines where under which positive or negative electrode this drug will be positioned to be carried into the human body. And you can see the purpose, the condition where that or another, at what that or another drug is the most effective to treat the patients at these conditions. And it is understandable that the problems by iron topophoresis can't be avoided, and you can see the list of that problems. And now let's recognize one more: human body electric processes, physics aspects, and these processes quantification. Look here, about 70% of the mass of the most vertebrates is comprised of the water distributed in the body fluid compartments. So, what are that kinds of the location of the water? Intracellular fluid, extracellular plasma, and interstitial. The transcellular this is one more body fluid compartment. And the body fluid compartments, body fluid compartment, and the volume of the water into that compartment is represented by this table. You can see this table compare these two specimen, I may say so, and the total amount of the volume in liters over 100 kilogram body weight. It is the relative amount of water into the compartments. Electrolytes composition of extracellular and intracellular fluid compartments of humans is of these. The extracellular fluid is composed of these ions of these concentrations. Two cell membrane transport mechanism of electrolytes are an active transport and diffusion. So these ions are present at the at biological liquids and make biological liquids as electrolytes. And these ions are transported through the membrane. And there are two transport mechanisms, active and passive, active transport and diffusion. Diffusion and the active transport, these two mechanisms develop two combinations of ions inside and outside of the cell of different ions concentrations. And what are the concentrations? One more time, shown by these two tables. And you can see that the resultant electric charges inside and outside develop the resultant electric fields, and because of the more number of the negative charges inside the cell, the electric field is different relatively to the electric field outside of the cell because of the greater number of the positive charges. And consequently, placing two electrodes inside and outside of the cell, the potential difference of this electric fields may be measured. It is the voltage. And when electrodes are connected to the voltmeter, voltmeter shows this for the nerve cell minus 70 millivolts voltage at inside and outside of the nerve cell. And this is termed in physiology as cell resting membrane potential. The Goldman-Hodgkin-Katz equation predicts actual membrane potential for a cell that results from the contribution of all ions that can cross the membrane. You can see that equation, and what is this? It is the membrane potential in volts equivalent to joules per coulomb. Symbol P denotes the permeability for the ion. These permeabilities for the different ions are different. So this should be taken in account when we estimate how many that or another ions go through the membrane. This process is allowed process. It is not random. So, and look, quantification of that electric property of the cell membrane to store different and to store different ions with different concentrations inside and outside of the cell. So look, you can see that resistor and capacitor, and this electric circuit is the physics model to describe the electric property of the membrane to store and to allow the electric currents developed by the flow of the ions to cross the membrane. You can see how poor, how bad is the membrane as the conductor because of this great resistance of the membrane. And it is not a good capacitor as well because of this small magnitude of the capacitance of the membrane. And one more characteristic of the RC circuit, it is the, one more time, let me pay attention. This is the physics model describing the property of the membrane. It is the time constant. If this circuit would be connected to the external battery, time constant shows how much time is required, is taken to charge the capacitor through the resistor up to its 33% of the final magnitude. And this time constant is very small for the membrane. It is of the 3 milliseconds. And look by how the resting cell membrane potential can change when the stimulus of threshold magnitude subjects influences the cell membrane. This opens the sodium channels and sodium goes inside the cell. Sodium carries the positive charge, and the flow of the sodium ions exchanges the negative sign inside the cell from to the positive, from negative to positive, and this is the depolarization. As fast as these channels open, they start to close after the charge inside the cell becomes positive, and potentials difference between the cell and the surrounding becomes to be of 30 millivolts. This is the signal for that voltage regulated channels to close. But potassium channels continue to open, and positive charge is removed by potassium from the cell, and the negativity of the interior of the cell is returned. Moreover, the flow of the potassium out of the cell increases the negativity and the cell membrane potential, and it is the repolarization, and the next phase is the hyperpolarization. And this short-lived change of the voltage at the membrane is termed as the action potential. In particular, this action potential for the nerve cell is shown here. This is the graph illustrating by how at the nerve cell, after subjection of the stimulus, the voltage changes over the time. This is just the action potential. What is this? Actually, it is the nerve impulse generated by nerve cell in physiology language, and this is the stimulus. It is the signal for the excitable tissue, in particular for the skeletal muscle tissue, to be initiated to contract. But the signal should be delivered to the effector. And for this, there is the long ending at the nerve cell. But now let me show you one more time the human nerve cell membrane action potential illustrations. Nerve muscles and some glands share electrical excitability, which in response to stimuli, rapid changes in membrane potential. The action potential occur. Within a millisecond, the membrane potential changes from negative to positive and back. Look, the first resting cell membrane potential. After stimulation, the voltage changes, and this is taking place within only 5 milliseconds. 0.5 millisecond. 0.5 millisecond. And hyperpolarization duration is of 4.4 millisecond. Why this happens? Because of the change over the conductance, permeability of the membrane for sodium and potassium. So, and look here, you can see the nerve cell ending, that is axon. It is covered by the myelin sheath that is interrupted by the free spaces of the axon, that is termed as nodes. The myelin sheath cover is of these 2 millimeters length, and this is of around 1 micrometer length, the node. And by how this process of the propagation, of the conduction, of the conduction, of the action potential may be modeled. Look here. This fragment of the free space at the axon generates the action potential. And this works as the battery with a closed switch to start to charge the axon. Next free fragment that is considered as the capacitor. You can remember that this membrane separating positive and negative, and this is considered as the capacitor. Exoplasm is modeled as the resistor for the charge to go along this fragment covered by the myelin sheath. So after the charge at the capacitor at this node of Ranvier reached 63% of its final magnitude, this triggers the generation of the action potential here, and the process repeats. And this time of triggering of the action potential at the adjacent node of Ranvier is of 40 microseconds. It is very short time. The length of this covered is taken as 1 millimeter. It's true. And the velocity of the propagation is of 25 meters per second. And the propagation looks like jump of the action potential from one node of Ranvier to another, to the adjacent node of Ranvier. It is the saltatory mechanism of propagation of conduction of the nerve impulse. And this is the physics model, electrodynamics model of this process at the axon. And this is just the explanation why and quantification of the process of nerve impulse propagation with this such big velocity. It is very fast process. And the next, look here, one more example of the excitable tissue that requires the electric impulse to initiate the function of that tissue. It is the cardiac muscle, and the group of the cells automatically, independently on the central nerve system, generates that electrical impulses, impulses that are transmitted and initiate the cardiac muscle contraction to compress the blood into the chambers of the heart and provide it with the mechanical energy required for going through the circulatory system, And this is the example of the excitable tissue. And look what are the action potentials are produced by different kinds of the cardiac muscle cells. And you can see how different are these action potentials from the nerve cell action potential. Why it is so? Because of the presence of the calcium. Calcium, it is the muscle, don't forget. So calcium contributes the action potential's magnitude and the shape. And this plot is just reveals the presence and contribution of the calcium. And this resultant action potential is recorded and is termed as electrocardiogram. Recorded resultant action potential generated by the groups of the cardiac muscle cells is termed as electrocardiogram, and this change of the voltage over time reveals the process of the propagation of the excitation through the cardiac muscle that takes place when within, as in this particular case, within one completed cycle of the function of the cardiac muscle. And you can see that electric dipole is taken as the physics model to explain that different recordings that are done by three pairs of the electrodes that are placed on the surface of the body at the limbs of the body. And these three pairs is termed as bipolar limb leads. Bipolar limb leads. Two electrodes develop the first lead, lead 1, lead 2, and lead 3. And electric dipole may be taken, I repeat, as the model to describe the propagation of the excitation through the cardiac muscle. We can imagine the surface separating two parts of the heart, the depolarized part of the heart and non-depolarized. And at each fragment of this surface, we can reconstruct elementary electric dipole with their electric dipole moments, and we can reconstruct that elementary dipoles moments into resultant vector, of the equivalent dipole, and this vector change in magnitude and the direction is the measure of the voltage change with time. You can see the voltage depends on the position of the electric dipole momentum into the space and depends on the magnitude of the electric dipole. And in correspondence to this, the voltage change are different over time for different limb leads. And look, attaching electrodes to the body surface allows the voltage changes within the body to be recorded after adequate amplification of the signal. Galvanometer within the ECG machine is used as a recording device. Galvanometers record potential differences, voltage, between two electrodes. ECGs are merely the recognizing of differences in voltage between two electrodes of the body surface as a function of time. Look here, the pair of two electrodes connected to electrograph with a wire constitute a lead. Types of lead: limb leads, bipolar leads, and unipolar leads, and chest leads. To investigate, to recognize more detailed the functional state of the cardiac muscle. The electrodes are placed at chest, just over the heart. And this gives extra information, more detailed information about functional electrical activity of the cardiac muscle. And look here, it is the recording of the voltage over time, change of the voltage over time, obtained through the first bipolar limb lead, through the second bipolar limb lead, and third. You can see how they differ from one another. And these are the unipolar leads recordings for detailed investigation of the functional state of the cardiac muscle. And fragments of the electrocardiogram are denoted by letters, and this smooth line fragment looks like a wave, and it is named as the P wave, reflecting the propagation of the excitation through the atria. Then excitation is stopped by the atrioventricular node to give the time for the blood to fill the ventricles, and only after this excitation goes through the ventricles, and this is reflected by this change of the voltage over time, and this fragment is the QRS complex, consisting of 3 peaks: Q peak, R, and C. One more time. Time is required to eject blood from the ventricles into arteries of two circulatory system, pulmonary and main, and systemic circulation, and this is the repolarization of the ventricles. And then cycle starts one more time, and this is just one completed cycle of the function of the heart. The electrocardiogram is analyzed in complex with the duration of the fragments and with the amplitude, with the maximum deflections of the voltage from the zero value. The ECG is recorded at special paper, ECG paper, with special speed of motion of this paper, and this gives the possibility to make quantitative analysis and diagnose, evidence diagnose of functional state of the human body heart. And look, you can see that data of the amplitudes and durations are compared with the standard by the experienced doctor's eyes, can look at the electrocardiogram, and eyes will analyze the shape of the ECG, and doctor can predict the presence or absence or something like this of the destroyer of the heart function. And finally, let's summarize that we considered. Physics models and methods objectively assess the degree of risks of exposure of external electromagnetic factors on the human body. Physics methods of exposure to electromagnetic factors with reasonability selected parameters have a therapeutic effect on the human body. Physics models and methods quantify the parameters of the dynamics of the life processes of electric nature and allow objectively and evidence-based diagnosis of the human body. And finally, this is the bibliography of the scientific resources of scientific information. The lecture time is over. We finish. Thanks for your attention.